This comes out of section 10.4, areas as limits. So in the last example we looked at the area under a parabola and said we could estimate it by dividing that area into a whole bunch of little rectangles and either overestimate or underestimate slightly depending on which side we measure from. If we do above or right-hand endpoints or left-hand endpoints and have a picture that looks something like this, you can imagine or picture that the more rectangles you did, if you divided your interval into, instead of 4 rectangles as we did in the last example, if you divided your interval into 1,000 tiny little rectangles, you would expect you'd have a more accurate estimate, and that's definitely true. The more rectangles you did this, if I had my parabola here and I divided this area into thousands and thousands of those little rectangles, my estimate gets closer and closer to the actual area that's under the curve. So that is in some way where they come up with the idea of integrals and areas under curves. They call it the method of exhaustion somewhere in your book, which I thought was quite fitting, because if you imagined dividing this area into 1,000 rectangles and then finding the area of each of those 1,000 rectangles and adding them up, it's quite ridiculous. Just to show you a bit of notation here, I just want to review something that is called sigma notation, and it's in the pure Math 30 but not in the Math 30-1, so some of the people in the class for the first year or two are going to have it, and then as we go along in the new curriculum nobody will have seen this before. But what this means is you're going to add up a bunch of things, and so they'll tell you where to start, they'll tell you where to finish, and they'll give you some kind of expression here, 3 times 4 to the n, let's say. So what is that telling me to do? If you've never seen that before, it looks awfully confusing. It looks like another language, because it kind of is. It just says start with 3 times 4 to the 2 and then keep going up until you get to the number that's on top, which is a 5. So I would be being asked to add these numbers together, whatever they happen to be. The first one's 48 plus 3 times 64 plus. If they change that to, n equals 1 and a 6 on top and left this thing the same, I would just start with 3 times 4 to the 1 and continue adding terms until I got to a 6 on the top. So I'd have more terms in this next one because I'm starting at a lower number and finishing at a higher number. And so this is what sigma notation means. Just means add up a bunch of terms. The area under a curve basically can be written as a fancy sigma notation to say, okay, we're going to add up a whole bunch of little rectangles. Each rectangle is going to be delta x units thick and f of x units high, and we'll have a bunch of separate little f of x's because we'll divide this from I equals 1 up to n, so we'll divide it into n little intervals. The example we did in the last one, we only divided it into 4 intervals, but the actual area is going to be the limit as you take n to infinity. In other words, if you could actually do infinitely many rectangles under this curve between 0 and 2 and add up the areas of all those slivers, you would end up with the actual area. Delta x is equal to the width of each one. So if you take b minus a and divide by the number of rectangles, and xi is just starting from your first spot. And so if I show this as a picture here, a up to b, we're saying if we divided this into n rectangles, each one is going to be delta x units wide, delta x units this way, and if this is f of x, each one of these is f of x units high, depending on what x is at each spot. So xi is going up in increments of delta x. All of that business we're not going to be tested on here in this course, but that leads to where we're going, a notation of basically the fancy sigma notation leads to this integral sign that says from A to B, we take f of x dx, and we're able to find areas under curves. And again, the book, I guess, just as I do, has a hard time deciding what to teach first and where to begin with this stuff, because there's background and then there's learning how to do antiderivatives. But basically, we'll be going forward with integrals and finding areas. We won't do any of the limits and sigma notation in this intro course, but you definitely will, if you go further in calculus, be very likely to run into a lot of sigma notation there.